Hello again everybody, welcome to the class. So, we had started a discussion on the secondary structure of proteins, right. So, as usual we will just do a quick recap. So, last time we had talked in some detail about the Ramachandran plot. I know we talked about the torsion angles, we saw what the angles were, what they represented, and how you could visualize the angles, what the different values of the angles meant when we were looking through the Newman projections. Then we went ahead and looked at also looked at those things in some details, right. And so, the Ramachandran plot essentially what it tells you the allowed psi and phi values. So, this is your psi in degrees and these are phi in degrees, okay. And so, then you plot them and you for a particular structure you have a psi value and a phi value for the different amino acids, right. And so, what you can see here is this say if you look at this is essentially the helical region. So, and if you look at this area on the top, this is if you follow my arrow, this is your beta, right, the beta sheet mostly, right. Then to the right you have the alpha helix, but this is a left handed alpha helix. Generally all the helices, most of the helices are right handed, and this is the extended chain. And then we went forward, and what we saw was, well, before going forward. So, this is G. N. Ramachandran, who actually got this plot or derived this plot, and what he said was then that the red regions are those combinations of phi and psi which are sterically allowed, right. Allowed is the key word. Then if you look at the pink regions are the lighter regions which are surrounding the red regions. So, those means that there is some relaxation of steric hindrance, okay. And then we looked at the commonly occurring protein secondary structural elements as we were seeing. We will just go back to that slide again, and on the right. So, this is a small mistake out here. So, this should read as region. So, on the right shaded region we have the left handed helix, which is not so common, that is why it is really observed. So, again if you go back, as I was saying, one more, this was the red region, this is the red region for the beta and all beta ensemble, this is the red region for the alpha ensemble or the helical ensemble, and then these are the pinkish regions which are some relaxation is permitted, okay. That is what we had said. And then there are some other aspects of the Ramachandran plot. For example, the atoms, when Ramachandran did that, he treated the atoms as hard spheres, okay. So, it is essentially these these are not soft potential, this is a hard potential, that is what we call it. So, that means you cannot squeeze this phase, these just collide, move apart, that is where the steric thing is coming from. Based on that, the psi and phi angles which cause spheres to collide correspond to sterically disallowed conformations of the polypeptide backbone, and hence you get those shaded regions of the plots which or where the psi and phi values are allowed, okay. Now, let us talk about protein structure. So, this also we looked at. Anfinsen, he won the Nobel Prize in 1972, and what he said was that the final structure that the protein is going to get is encoded in the primary sequence, which is the way the amino acids are arranged, right, the sequence of amino acids. So, what the protein he took, this was the major protein he took, it was bovine pancreatic ribonucleus, and then we talked about these two experiments, right. So, in one case there are 4 disulfide linkages, he reduces with mercaptoethanol, then denatures with 8 molar urea, then he removes the urea, oxidizes it, and he gets back the native like activity. However, what he tried to do was he scrambled it in the next experiment. That means, he reduced the first step remained the same, right, this step remains the same as the previous one, and here now before removing urea he actually oxidized them. Now, because it was a denatured protein, so what happened was not all the sulfur SH groups were in the proper orientations, right, obviously they were not, because it is a denatured protein, you have 8 molar urea in it. So, what he managed to do by oxidizing, he managed to scramble the disulfide bonds. So, he had many different disulfide bonds formed, and as a result what happened was when he removed the urea now after oxidation, what he found was the scrambled one was only 1 to 2% active. That means, the protein had not achieved its native state, and only because only 1 to 2% of the protein molecules actually had the correct conformation, which could carry out the enzymatic activity. But then a clever thing that they did was that on this they added a little bit of reducing agent. So, the reducing agent what it allows you to do is it reduces this disulfide bond, so goes to SH, and then now it can scramble in the sense now it can exchange, right. And once the exchange happens, what he saw was after giving it some certain amount of time, then the native activity, native like activity slowly comes back. It almost reaches the activity in its native state. So, this led him to propose the hypothesis, which he said that the 3-dimensional structure of a native protein in its normal physiological milieu is the one in which the Gibbs free energy of the whole system is the lowest. That is, that the native conformation is determined by the totality of interatomic interactions and hence by the amino acid sequence. So, what would define the interatomic interactions? Those would be the amino acid sequence, because that is where the interactions are coming from in a given environment, right. So, this is the so called thermodynamic hypothesis as proposed by Anfinsen and his co-workers, right. So, this is until what we had covered in the last class. So, let us move on now. Let us actually go deeper into the secondary structure, start looking at different components of the secondary structure. So, first question, remember when we started talking about proteins, the first question we asked is or was, why do we need proteins? Here we ask the same question, why we need a secondary structure, or why should we care about a secondary structure. So, let us look at it. See, myoglobin is a protein of which, or is that protein whose crystal structure was solved the first by Kendrew. Okay. So, what they saw was, or what Kendrew and co-workers saw was, when the crystal structure was solved of myoglobin, that means it was observed that the interior of the protein almost exclusively had hydrophobic amino acids. Okay. Now, what does it mean then? See, remember, if you go back to the previous class where we are talking about the different amino acids, you have polar, non-polar amino acid like hydrophobic amino acid side chains essentially, right. And so, what they saw was that all this, I mean, in the interior of the core after it is folded, right, because it is doing like a crystal structure of the folded protein. So, the interior mostly has hydrophobic amino acids. So, what conclusion they reached was that thus the main driving force for the folding of water soluble globular proteins can be considered to be the packing of the hydrophobic side chains, creating a hydrophobic core. Now, this hydrophobic effect or hydrophobic core we would look at in more details a few classes ahead, but let us just take it very simply and see and think about it. What has happened is that if you have taken myoglobin, it is soluble, you pour it in water, right. Now, what will happen is the hydrophobic amino acid side chains, they would not like water. So, they would try to move away from water, and once they move away from water, what they would do is they would try to go inside the interior of the protein, being surrounded by the other polar amino acids, right, or charged amino acids. So, that is exactly what has happened. That means, the core of the protein is essentially hydrophobic in nature. Okay. So, what is the consequence? Now, if you think about the peptide backbone, right, it still has these NH and the CO groups. So, that is what it says. The main chain has NH as the hydrogen bond acceptor and CO as a hydrogen bond donor and CO as a hydrogen bond acceptor. So, they are still there. Now, remember your core is hydrophobic, right, but then the core has to be made of amino acids, right. It is only the side chains that make them hydrophobic, but you still have this NH and CO groups. So, hence in the hydrophobic core, the main chain polar groups need to be neutralized. What do I mean by the main chain is it is essentially the peptide backbone. So, you have this NH2 group and the COOH group. So, then if you remember the way the peptide bond was being formed, N makes a nucleophilic attack on the CO, there is a loss of water. So, one CO stays and there is one NH out here. So, this NH and CO, this is from the peptide backbone, it still remains, right. But when you form the hydrophobic core, you cannot get rid of this, these are polar. So, that means these polar groups are still there in the hydrophobic core, and these polar groups need to be neutralized. So, thus hydrogen bonds form between these polar groups, right, simple. So, that means if the charge has to be neutralized, or if that polar character has to be neutralized, you better form a bond. So, the bond they form is the hydrogen bond, and this is very important. The formation of regular secondary structure arises from the need to avoid a huge solvation penalty in the nonpolar core. Okay. Think about the statement again, it is very important and very significant statement. This is why we have secondary structures arising from regular hydrogen bonding patterns. What is the secondary structure due to? The formation of regular secondary structures arise from the need to avoid a huge solvation penalty in the non-polar core or the hydrophobic core, because in the hydrophobic core you would rather not have these NH and CO groups dangling around, right. Their polarity or their charges have to be, or even their partial charges, those have to be neutralized, and that is how the hydrogen bonds are found, and that is why the hydrogen bonds are found, and that is why you get secondary structures. Okay. So, this is the importance of secondary structures, right. I mean, this you should really keep in mind. So, what are the different sorts of secondary structures? Okay. Then the types of secondary structure. So, obviously, these are local structures that are stabilized by hydrogen bonds. These are local, because remember the first level is the primary, then you form the secondary, then the tertiary, then the quaternary. So, obviously, these are local structures, means the hydrogen bonds are forming locally, that means between adjacent or nearby residues, not exactly adjacent, but nearby residues. Okay. The first one, possibly the most common one, the alpha helix, then you have the beta sheet, which is composed of beta strands, then you have turns, right, beta turns or beta bends. We will take this individually, and what you will see today in class is we will mostly focus on the first one, which is the alpha helix. So, let us go on to it. So, this is the alpha helix we are talking about. This was first proposed by Linus Pauling and Robert Corey in 1951. Now, it was identified in keratin by Max Perutz. It is the most common secondary structural element of proteins, that is what I was just saying. Stabilized by hydrogen bonds, we will soon look at the hydrogen bond pattern, this is a famous pattern. Then we go and look at the right handed alpha helix. Okay. So, this is what typically alpha helix looks like, right. This is your alpha helical arrangement. Okay. What do we see? The oxygen atoms, they are in red, then the nitrogen atoms, they are in blue, then the carbon atoms, they are in black, and if you look at these white ones, the white small squares, these are the hydrogen atoms. Let's go with, these go without saying, right. So, if you look at these things, these are essentially the hydrogen bonds that are taking place between the I and the I plus 4th residue, right. Some other characteristics of the alpha helix, I am just giving a schematic of the characteristics, we will come back, because this is what we are going to discuss on or spend time on in this class. So, the helix is stabilized by hydrogen bonds, Hb stands for hydrogen bonds between backbone NH and backbone carbonyl atom. So, you can see this is carbon, right, this is the oxygen attached to it, and then you have this hydrogen bond, which is accepting the hydrogen bond from where? This is the H and this is the corresponding N. Okay. And you can see the residues, this is 9 and this is 5, right. So, that means remember I and I plus 4. So, this is 5 plus 4 is 9. Now, that is essentially what you are looking at. Okay. Now, these are some geometrical characteristics. So, alpha helices have 3.6 residues per turn, that means you complete one turn, you go from here to here. So, this is one turn from here to here, as it says, it has a 3.6 residues, you complete a full turn like this and you get 3.6 residues. It is a translation of 5.4 angstroms per turn, that means this is essentially a pitch, do not worry, I will come back to it again. This is the pitch, which is 5.4 angstroms, and hence if in one pitch of 5.4 angstroms you are having 3.6 amino acids per pitch or per turn, then obviously that means for each residue in the 3.6 residues per residue, I have a movement of 1.5 angstrom, right. That means the translation of 1.5 angstrom per residue. So, that means you have 3.6 residues, and when I go from the first residue to the second residue, I have a translation of 1.5 angstrom, the second to the third 1.5 and so on. Okay. So, this in a nutshell is your alpha helix, and also if you look at it, if you look at it like this, it just looks like a cylinder, is not it. Okay. So, let us talk about the geometry. Now, this is where it becomes really interesting. So, on the left you can see a continuous helix, that means it is just in continuum, there is no break. On the right what you see is I have put some spheres or some big dots or big circles. Now, these big circles can be considered as amino acids. So, essentially now the helix is not continuous. What I mean by not continuous is that means from here to here you have nothing in between, is not it. So, that means this, say this is the first residue, this is the second residue, this is the third residue, the fourth residue and so on, is not it. Now, let us look at these. I hope you are okay with this, right, no questions, right. Okay. So, just to make the point again, this is a continuous helix, means that wherever I move on this line, I have something. However, if you look at the right one, okay, if you look at this right one which is labeled as B, I have put in these circles. That means, from this circle to this circle, in between I do not have anything, it is essentially a discontinuous helix. Okay. Right. So, the characteristics of a continuous helix, let us look at it. It is characterized by the pitch p and the radius r adopted by the spiral, because it is a helical spiral, right. This is how it is going on, and it is going around the z axis. Okay. So, this is a z axis. So, like if I take a pen, if I take a pen like this, if I take a pen like this, if this is my z axis, then the helix actually is moving around the z axis. And if you can see, from your side, it will be different if I look at from my side. See, when I move from this side, this to me is front, if you look at this finger, but to you is back, right. Then I go like this, I go like this, I go like this, then it becomes in front, and I come back here. This is my one turn. Okay. So, then this is what P represents. This P essentially is the pitch, it represents one complete turn. So, you can see I started from here, right, I made one turn and I came back to the same position, but I have translated by this amount of P, which is the pitch. Okay. So, how we can describe the geometry of the helix, right. See, we will talk about this in more detail. So, do not worry, I do not think you are getting lost. Even if you are getting lost, we will find you. So, do not worry about that. So, we can describe it with the help of a Cartesian coordinate like the normal x y z system, or we can use a cylindrical coordinate, r j z. I will tell you what these are. These coordinates are this r j z, and in either case whether you take x y z, that means the Cartesian or the cylindrical, this one in between, that is in the middle, is essentially your z axis or the helical axis. It is also referred to as, please keep in mind, the screw axis. Okay. So, whatever we do, I have the axis that around which the helix is developing. Okay. Now, let us look at this. Each sphere, as I was saying, so this is the second figure. Each sphere can be considered as an amino acid. It is good. Now, what is delta z? Delta z is the extent of translation along the z axis, also known as the helical rise, that is a vertical rise per residue. Now, look at it very carefully. So, suppose I am moving from, this amino acid to this amino acid. Okay, you follow my arrow from this amino acid to this amino acid. Now, what I have done is, see, I am not on the same plane, that means I am moving, but I am also translating, I am also moving up, like it is not moving like this, it is actually moving like this, right, it is moving like this. And hence what you see is, if this is what the value along the z axis is, then for this one it has moved by this amount. Okay. So, it has moved from here to here after going to the next residue. That means, as I move from here to here, I have translated in the vertical direction, that means along z by a unit of delta z. So, that is what this delta z or delta z is referring to. That means, that it is the amount of vertical translation I am having per residue movement. I move from one residue to the next residue, delta z is the amount of transition I have moved in the z direction. Okay. And then what is delta phi? Now, keep this in mind, I am moving like this. So, not only am I moving up, I am also rotating, right. So, I am also moving angular in an angular fashion. So, then what is delta phi? So, you look at this. So, to get delta phi, essentially what you are doing is, you look at this first amino acid and you look at this one. What you do is, so this is the xy plane, right, and this is z axis. Okay. Say the first residue is essentially on your plane, right, and the next residue has actually moved up like this. So, how to get the angle between this? You draw a projection from this residue onto the xy plane. So, that is exactly what I have done. What I have done is that, remember, from when I went from here to here, I have already moved by delta z. Okay. So, this is from here to here I have moved, that is my delta z, right, from here to here. So, it means I already moved up. So, now I cannot place it in the plane, but what I can do is I can draw a projection, and so this is my projection, you see this red dotted line. Now, this is the xy plane, right, this is y, this is x, this is xy plane, and what I do is, now I connect to the origin, and this angle, that means the angle which this projection of the second residue makes with the first residue is refer to as your delta phi. So, this much rotation you have done on moving from one residue to the next one. So, there are two very important components. What are the two important components? One is delta z, that means the vertical translation, and the other one is delta phi, that is the rotation as I move from one residue to the other. So, in a helical movement, what am I doing? I am doing two things, simple, I am rotating and I am also translating. That means, if I ever have to bring about a coordinate system or try to get the geometry, I need essentially two operators. One is a rotation operator that will cover my rotation, and the other one is a translation operator that will cover my translation right along the z axis. Then there are some key points. Combination of, as I just discussed, combination of incremental translation and incremental rotation as one moves from one helical residue to the next. So, this is what happens. So, to get helical symmetry, I need a combination of incremental translation, which is delta z along the vertical axis, and incremental rotation, which is delta phi, as one moves from one helical residue to the next. Okay. What is P? P is the pitch of the helix, that is the vertical distance that has to be travelled to make one complete turn. Remember, I was telling you have this, then you move from here to here, you make this one complete turn and you come back here. Then what is R? It is the distance of a particular helical residue from the z axis on the xy plane, right. All identical units are at the same distance r from the helix axis. I will just show you, I will go back and show you what I mean by this. And what is P by delta z then? Remember, delta z is the vertical rise per residue. What is P? P is the total rise I have gone through during one complete turn. If I need to know the number of residues which are there in making one complete P, then what do I need to do? I just need to do P by delta z. So, that means the number of residues per turn of the helix is given by C, which is equal to P by delta z. Okay. So, this is what I meant when I was talking about let us see. Yeah. So, this is what this was what I meant when I was talking about R and P. So, you look at this, this is P, you are making from here, you are going here, it is one complete turn. Now, the R thing, so this R is, you look at this one, does not matter what which one you are looking at. So, you can see this is my z axis, right, and suppose this is the residue, this residue. So, you can consider this xy plane. So, this sections of the xy plane like this, you are going like this. So, this is the distance this residue has from the z axis. That means, this is the xy plane, this z axis. If the residue, if the z axis, if the residue is somewhere here, like this is the z axis, right, xy plane, the z axis. If the residue is somewhere here, then from here to here, the distance is essentially your r. Okay. Now, what we will do is we will just make a small change of gears. I will be using the I will be writing something down, so that it is better for us to understand. So, what do I need? So, then what I can say is, let us talk about cylindrical coordinates. Okay. So, let us talk about cylindrical coordinates. Now, in cylindrical coordinates, what we remember, what we had is that the z axis was essentially my helical axis or the screw axis, is not it. Now, you have so many residues. Okay. So, what can I do? So, what I can do is, say suppose I have many residues in a helix, right. Then what I can write is, say suppose the z coordinate, right, the z of the jth residue. So, how many residues? Say I have j, j plus 1, j plus 2, j plus 3 and so on. So, what I can have is this is what I can write. I can write is j times delta z plus delta z. Okay. So, what do I mean by this? What I mean by this is this. So, suppose I have something like this. So, this is my this is my z axis, right, and this is my x, this is my y. Okay. Just a rough schematic. So, this is how I am moving. So, I am moving like this using my helix. So, now what I can do is I can put my amino acid, say one amino acid is here, one amino acid is here, one amino acid is here. Now, this is a very rough schematic. So, please keep that in mind. Okay. Now, what can I do? So, suppose this is my first amino acid. Remember, we talked about R. Let me show that to you. So, this, if I drop a line on the xy plane, remember this x, this is the xy plane, right. I drop a line. Now, then what I do is I connect this. Okay. Now, once I connect this, what do I get? This distance. So, you see, this is the projection of this amino acid, right. So, if this is the projection, see, this is the projection. See, if this is the projection, then of this amino acid, then this distance is r, as discussed in the previous slide, and you talk about this angle. Okay. So, this angle is essentially your delta phi. Okay. So, that means, whatever it is, as I am moving from one residue to the next, okay, this is the type of angle I am moving through. Okay. This delta phi is essentially the angle it is forming with that axis. Okay. Now, what else can I put in? What I can put in is, this is my z of j, that is the z coordinate, but okay, let me tell you what j is. J is essentially the j backbone residue. Okay. So, that means I have say j minus 1, j minus 2, j minus 3 and so on, right. So, when I move from one amino acid to the other, I move by delta z. If I move by 2 amino acids, I move by 2 delta z. If I move by j amino acids, I move by j delta z. And what is delta z? The delta z is very simple. So, if you look at this one, right. Now, this one, what has happened is this this first amino acid. See, this first amino acid is not starting from the xy plane. So, it is at a distance from the xy plane, right. So, that means the z, it already has some z value, and that, or some distance, some vertical distance as a z. So, that is what I have represented as delta z. Okay. So, this is what the delta z is. See, from here to here, this is what your delta z is referring to. Okay. Now, the way I look at it, or the way we can formulate is, once we have the z coordinate, we can also go with the x coordinate. So, the x j, how can I write it? Now, this is where the cylindrical coordinates are coming in. So, I can write this is r cosine 2 pi delta z over p, right, plus delta phi. And then say I move to y now, how can I write y? So, I will write y a little bit down here. So, y I can write r sine 2 pi then delta z by p plus, so this is delta phi. Okay. I am just running out of ink, but I will just use this. So, this is I think you can recognize this is delta, right, and this is delta, this is phi, this is 2 pi and this is p. Okay. So, that means what I have done is I have been able to have a coordinate system where z is given by this. Remember, j is the residue, amino acid residue. Okay. Then I have x of j and then I have y of j, right. What do we do next? What do we do next is, you just look at a simple feature of this. Now, what is the simple feature? The simple feature is, see, for example, if I do this, now keep this in mind though. Okay. If I do this, what will happen? What will happen if my r is 0? What will happen if my r is 0? Okay. If my r is 0, now look at this. Okay. Z is z, that is fine, Z remains the same. No change. Okay. So, what I do is, then because there is no change, what essentially happens is it is not no change, then what it will happen is it will go as delta Z, right. Say I am moving one residue by 1, then x transforms as x, y transforms as y. Why is it so? Because you look at this x and y, x has r times something, y is also r times something. Now, you are saying that r is 0. So, if r is 0, essentially what is happening? If r is 0, there is no distance of that residue, that means the r is 0, that means this quantity is 0. So, that means there is no distance from here to here. So, essentially r being 0, that amino acid or that residue is falling on the z axis. So, if it is falling on the z axis, what do you get? So, essentially what you get is you get a linear structure, right, governed by translation of delta Z per residue along the Z axis. Okay. So, this is what I have. Now, this is in cylindrical coordinates, right. Okay. I hope you understand the significance of this. So, Z vertical, then we have the xy plane, we have these to define. Now, what we will do is we will take a look at the Cartesian coordinate system. What can we get from there? So, when we will talk about a Cartesian coordinate system, now this is what we do, right. We talk about a Cartesian coordinate system, then in the Cartesian coordinate. So, we can write using I am trying to use Cartesian coordinates, right. If I am trying to use Cartesian coordinates, what we know is, we know that in helix, what do we have? We have rotation plus translation, isn't it? Now, once we have that rotation and translation, this is a combination. So, your helix is what? Essentially a combination, right. That is why I have written the plus sign. Now, if I am having the combination, what am I going to do? So, if I am having the combination, then what you would understand is this, I would be having a rotation operator, and here I would be having my translation. So, if that is true, that means I need a combination of two operators r and t. So, if that is true, what can I have now is, then if I have to move, say I have to move from ith residue or jth residue to I plus 1th residue. Okay. This is what I have to do. Now, if I have to do that, what I can, how then, that means what I am looking at is, say my ith residue initially has these coordinates I. Now, I move to what? I move to x, y, z I plus 1, x, y, z I plus 1. The question is how? Well, you know the answer, it is a combination of rotation and translation, isn't it? So, what I can write is, I can have my rotation operator, rotation x, y, z, then I plus I have my translation, right. I am translating along the vertical axis. Now, this is going to give me x, y, z coordinates of I plus 1. So, see what I am trying to do is, if I know the coordinate of 1, that means if I know the coordinate of any atom in a helix, and I know that it is sitting in a helical symmetry, it is part of a helix, then As I move from here to here, that means I move from I to I plus 1th residue, that is the next residue. Can I get the coordinates, and like this can I get the coordinates of the whole helical system, right, whatever amino acids are being a part of the helix. Okay. So, then if that is what it takes, what we have to do, then what we can do is we define something we know from before. We define the helical rise, as delta z, that is what we have defined. Okay. We have defined the helical twist, we have defined the helical twist as what? We have defined the helical twist as very simple, delta phi. So, once we have defined the helical twist as delta phi, we have this, right, not a problem. Then we also know some other things. What do we know? What we know is that your pitch, that means your total translation in one repeat is equal to, or one turn is equal to the number of repeats, which is C times delta z, right. Now, what you do is, if I start looking at the coordinate system, what can I do? Remember, I have to do a rotation and I have to do a translation. So, I will just go over to the next page, because I do not have much space here. Then what I can write is, I can write a matrix representation. So, this is what I can do. So, I can write cosine del phi. Okay. So, then I can write minus sine del phi, then 0, then sine del phi cosine del phi 0, then I have 0 0 1. Why? Because this is the rotation along the z axis in the xy plane. This I multiply on the coordinates of the ith residue. Now, once I have done that, remember what delta phi is. Delta phi essentially is the angle between the two helical residues. That is what that is how much I am moving by. So, if delta phi is if delta phi is the angle between the two residues, then I have just done a rotation, but I need a translation. So, to do a translation, what I will need is I will just move along the z. So, this is what I will do. I will do a 0 because I am not moving, I am not translating along the xy plane, but moving along the z axis, and hence I am moving by delta z. And if I do this, then I get my coordinates of I plus 1. Okay. So, I hope you follow what we have done. So, we start from the very first thing. So, see, this is what we did. Okay. So, this is what we did. Just be careful about one thing though, that this angle, this angle is essentially the angle it is forming. So, when I talk about delta phi, when I am talking about delta phi, I essentially what I mean is, this delta phi is actually the angle between the two residues. That means, you move from one residue to the other residue, this is what you get. Okay. Now, the z coordinate j, the number of residues you are going to look at, or that means the number of residues are going to move from here. So, if I move from here to here 1, that means j is equal to 1, this plus delta z. Then I have x j, this is r cosine of 2 pi delta z by p plus delta phi. So, here this when you talk about this delta phi, just keep this in mind, that this what do I mean by this delta phi? This delta phi here actually has a different meaning. So, this delta phi is, suppose this is already what I have here. Now, this delta phi is essentially what you are seeing is here. Okay. So, this is this is what I am looking at, this angle. So, I would be let me change it, let me change one thing. So, what I will do is, instead of doing delta phi, what I can write is delta phi, I should maybe I can write, well, I can keep it as delta phi I, okay, or delta yeah, let me just change it. So, let me do this delta omega, let me do that. So, this is actually delta omega, okay. Let me change that. So, what is so this one also would be then referred to as delta omega. Okay. What I mean is, because there is no amino acid here, please do not get confused by this. It is just the angular orientation from with respect to the y axis. So, but the delta phi that I am actually talking about is the angle, if you remember what you had seen in the previous one. It is the angle essentially what you are it is very simple. It is the angle essentially what you are plotting is between this guy and this guy. So, that means here you have a projection out here, here is a projection out here, this is the amount of angle you have moved, and that is what delta phi is. Okay. So, this delta omega I can just represent as phi, because I was looking at phi, and this is also phi, and I can take this as phi. So, what I am saying is that this angle which this amino acid projection is making with y is phi, and then when I am moving to the next one amino acid, I am moving by delta phi. So, I had this phi and then I am moving by delta phi. So, that is what this is representing. I hope you are okay with this. So, what you do is you just replace this delta phi by phi or delta omega, does not matter, and here also you replace this delta omega or this delta phi by phi or delta omega, whatever it is just one angle. It tells you that this is the amino acid, this is at a certain distance from the y axis. Now, so this is the projection I mean. Now, from here I move to the other amino acid, that movement is delta phi, but the first amino acid makes a certain angle phi or delta omega with the corresponding y axis. Okay. So, now when we talked about, remember we talked about this matrix representation, that means we have a set of coordinates x, y, z for any residue in the helical axis or in the amino acid residue in the helix. I try to look for the coordinates for the adjacent residue. This is what I do, right. I do a rotation and I do a translation. Now, once I do that, I have some also other things in mind. What are the other things I have in mind? Okay. So, these are some of the other things I have in mind. So, the other things I have in mind is that for one p, it represents one full turn. Now, this one full turn corresponds to a 360 degree rotation or a rotation by 2 pi radians, is not it. So, that means remember the number of repeats or so the number of residues was c. So, what I can do is I can write this delta phi is equal to the full rotation is 360 degrees for one turn over c. That is my expression for delta phi or 2 pi over c. Okay. That is one expression. Also, I know p is equal to c times delta z, or delta z can be written as p by c. So, then what we can do now is I have this expression, I also have this expression, is not it. So, I can take these two expressions and then I go back to this matrix. In place of delta phi, I put in this 360 by c or 2 pi by c, and in place of delta z, I put in p by c, provided these are known to me. Good. So, that was the next step. Now, let us come to a normal helix or a regular normal helix means a regular alpha helix, that is what I am talking about. Now, the regular alpha helix we know. So, this is a regular alpha helix. What do you have in a regular alpha helix? We have, which is C 3.6 residues per turn. So, we know one thing, we know delta z, delta z is equal to p by c, right. Now, the pitch for a helix is, can anyone say, right, it is 5.4 angstrom, this is the total pitch. So, that means the delta z is equal to 5.4 angstroms over 3.6, which is essentially 1.5 angstrom, isn't it? So, that means what it says is that vertical distance I move when I go from one residue to the other, the vertical distance what I move when I go from one residue to the other is referred to as your your helical rise is 1.5 angstroms in a normal alpha helix. This is what P is. Okay. I pretty much have everything. Now, you see, now what I can do is, let me write the matrix again. Based on this, if I write the matrix, what will I have? I know what my delta phi is, right. Okay. I did not talk about delta phi here. So, did I? Yeah. So, now then delta phi, if you remember, it was 360 degrees by, this is 6 by C. So, essentially C is 3.6, then I get 100, right. Sorry, what I am right, this is 100 degrees. If I am writing 100 degrees, so that means now I have everything. So, what I do is I go back and I say this is cosine 100 minus sine 100, then 0, then sine 100, cosine 100, then this is 0, this is 0, 0, 1, do it on x, y, z of the of the ith residue. Okay. Once I do it of the ith residue, plus I have the translation. Now, what is my translation now? It is 0, 0, then delta z, and what is delta z for me? Delta z is 1.5 in angstroms. So, once I have that, isn't it? So, this is equal to my x, y, z, I plus 1. Okay. So, this is really significant. Why is it so significant? Because you see what you have done. What you have done is, I am taking this, I have one residue, I know, when I know one residue, then if I have to go to the next residue, how do I know the coordinates? I know the coordinates of one, now I do a transformation, that means a rotation matrix followed by a translation, I know the residue of the coordinates of the next one. Okay. In this way, you can generate the whole coordinate system of all the amino acids which are in that helical segment. Okay. So, a few more pointers on this. If you would sometimes see the symmetry of helix is often given as 3.61. Okay. So, that means I made one turn and I move by 3.6 residues, but integers are much better to deal with. So, what I do is I take this and I multiply by 5. So, what do you get? I get 18 5. So, what does this mean? It means that I have in 5 full turns I have 18 amino acids or 18 residues. I hopefully you will remember this exercise, and just before completing this exercise, I just want to take you back to that confusing thing which you still find might find confusing is this one which I was trying to tell you. So, again this guy you do not, it is essentially not delta phi, it is phi or delta omega, whatever it is. So, let us consider it as phi. Then when I move from here to the next amino acid here, that is my delta phi. Okay. So, that is why instead of delta phi you should be writing phi here. Okay. So, please keep it as phi. I might even remove delta omega, but well, let me do that. Okay. So, let me actually get rid of this delta omega, and let me get rid of this delta omega too, just keep it phi. This is also delta omega, this is just phi. Okay. Okay. So, that was about the symmetry operations that we needed to talk about, but let us come back and look at the slides. So, in the slides, remember where we were at this. See, this is the phi I was talking about, I missed that out because I thought that that is the mistake I did. So, this is phi, right, and then if I am going to move from here to here, that would be my del phi. So, that is what I am doing. So, essentially this is how I am moving. So, anyway, it does not matter. That means, if I am moving from this residue to this residue, now it is del phi. Okay. So, moving forward, then we can look at the properties now. So, this is, remember, the helix is looking, it looks like a cylinder. There is hydrogen bond between the I and I plus 4th residues, okay, between the CO and NH. There are 3.6 residues per turn. There are 13 atoms between the H hydrogen bond donor and acceptor. So, this is the hydrogen bond donor and this is the hydrogen bond acceptor, the CO. What are the Ramachandran angles? The phi is about this is some average values. Phi is about -60, psi is about -40. The hydrogen bond, the helical hydrogen bond, it happens between the CO of the ith residue and the NH of the I plus 4th residue, and it is essentially are most of the times always right handed. Okay. The geometrical characteristics we have just seen, the 3.6 residues per turn, right, first point. The next point, there is a translation of our 5.4 angstroms per turn, which is the pitch. The translation of 1.5 angstroms per residue, which is the delta Z or P by C. One turn corresponds to rotation of 360 degrees, right, a full turn. Then the helical twist is essentially delta phi, which is given by 100 degrees, 360 degree over 3.6. Okay. So, this is a regular alpha helix again. I can, if you remember the Ramachandran plot we had seen before, this is where the regular alpha helix comes, okay, having minus phi of -60 and psi of -40. So, this is phi just in the negative of phi, and this is psi. So, this is 0 and then the negative of psi. Okay. Helical handedness, I can have a right handed and I can have a left handed, as if you remember. So, if you this one is your left handed alpha helix, and mostly what we have is you can just look at how the left handed and the right handed differs. So, this is how the right handed and then you have the left handed. So, this is what we mostly encounter. Very rarely we have a left handed combinations helix. This is what the left handed helix is. Both phi and psi angles are in the positive domain. You can see phi is plus 60, psi is plus 40. Now, some more properties of the alpha helix. So, you look at this. So, this is I will just go through this one by one. So, this is some schematics. You can see the alpha carbon atoms. Here I can see these small arrows. Okay. These are the helical dipoles, right, the small dipoles of the individual peptide bonds, and this thick arrow is a helical dipole. And then here in the third one you almost see everything. Okay. So, let us look at what I am trying to say. Okay. The first one, in the first one what we have is we have only the carbon atoms, the alpha carbons, I mean C alpha. If you remember C alpha, this was what C alpha was for us. So, I am showing only the alpha carbons, is not it. Okay. Now, and also keep in mind 5 9 difference of 4 residues, 1 5 again difference of 4 residues, remember, and hydrogen bonds would be between I and I plus 4th residue. Okay. Now, if I look at the second one, so here these are the small dipoles of each and individual peptide bond, and then all these, since they are in the same direction, they sum up together to give this collective dipole. So, this dipole, that means the helix has a micro dipole. So, the individual peptide dipoles have been depicted along the backbone fold, as you can see. So, these are the individual helical dipoles, right. Then the thick arrow, which is the arrow in the middle, this thick arrow, this thick arrow represents the macro dipole of the helix, which is summation of all these small individual dipoles. As a result, what happens is, see, this is the N terminus and this is the C terminus. Okay. So, the N terminus is the positive end and the C terminus gives you the negative end of the dipole, right. Okay. The third one, remember, where we are seeing almost everything. So, these are the backbone hydrogen bonds which have been shown in red. Then the red's face, so that means these are the red's face, these are the red's face. These depict what? The oxygen atoms of the CO of the peptide backbone, that is the main chain. Then the oxygen atoms, what do? These oxygen atoms, they accept the hydrogen bond from this H attached to the N of the H, you mean the H of the NH group at I and I plus 4. So, if you look at this R 5, say this is I, then you see R 9, this H is hydrogen bonded to the CO of this R 5, the residue having the side chain R 5, this is I and I plus 4, 5 plus 4 is 9. The blue's face are essentially the backbone hydrogen atoms of the peptide bond. Okay. So, what do we note here? Special mention, the peptide group, it's actually group, it should be group, is running from the top of the page. So, that means, so this is R1, R2, R3, R4, so on. That means it is starting from the top and going towards the bottom. Now, what you get is at the N terminus, this is important, there are NH groups that are unsatisfied, that is not hydrogen bonded. Remember, all NH and Cl groups are not supposed to be hydrogen bonded. You can see here, look at this, 1, 2, 3, 4. See, these are without any hydrogen bonds to a CO group, because that is where your helix is ended. There are no other things out there. Similarly, a similar thing would be happen at the C terminus. So, you can see there are also oxygen atoms like 1, 2, 3, 4, which are free, which are not hydrogen bonded now. This gives rise to something, it is an important concept in protein structure, it is helix capping. That means, you have some residues either at the N terminus end or the C terminus end, which which help in neutralizing or forming hydrogen bonds with these unsatisfied donors or acceptors. We talk about transmembrane helices, because if you look at membrane proteins, there are essentially the segment spanning across the membrane is essentially transmembrane. That is what we call transmembrane. So, this is what we are talking about. So, if this is the membrane, okay, this whole thing is a membrane from here to here, right, and you can see these helices encompassing the membrane. This is called the transmembrane. This is of the protein Bacteriorhodopsin. Okay. Thickness of the membrane is about 30 angstroms. That is what we see out here. So, bilayer thickness. Now, to span the lipid bilayer thickness, the helix will need to be about 20 residues long, is not it? Okay, because it is about 30 angstroms. So, why does it need to have 20 residues long? Because remember, I move from one residue to the other, it is 1.5 angstroms. So, this is what I have, 20 times 1.5, which is 30 angstroms. Okay. Now, what do I mean the helical wheel? So, look at this. If I look at this helix from the top, that means this is where I am viewing it. I am viewing it from the top, right? I am not looking at it from the side. So, going back. So, this is you are looking from, and this is how it looks, right? So, you see R1, this is 1, then 5, 9. So, you see this R1, R5 and R9, these are almost on the same side, are not they? And hence, here also they are occurring on the same side. Okay. Then you talk about 4, 7, you can see 4, 7, they are occurring on the other side. So, there is a helical wheel. So, that means you are looking like this through the helix from the top, and this is how the wheel looks like. So, for short helices, the side chains that are 4 residues apart in the sequence tend to cluster on the same face of the helix. That means 1, 5, 9, see they are clustering in the same face, then 2, 6, then you can see 4, 7, right, they are kind of clustering on the same face. Okay. Or I can say instead of saying 4, 7, maybe 4, 8 is better, I plus 4. Remember, it is 3.6 residues per turn, right. So, okay. So, the periodicity of the alpha helix ensures that side chains that are about 3 or 4 residues apart protrude on the same side of the alpha helix, right. That is what happened, right, 4, 7, 4, 8. Quite a few helices have polar and non-polar amino acids distributed about 3 to 4 residues distant in the sequence. So, this gives rise to a hydrophilic phase and a hydrophilic phase, and it should be a okay. So, this should be hydrophobic. Let me change that. Okay, it is a hydrophobic phase, that is what it should be. So, it is a gives rise to a hydrophilic phase and a hydrophobic phase, that is called amphipathic, because it is amphi pi, that means it has both hydrophilic and hydrophobic phases. Now, such an arrangement can stabilize packing of helices and is very well known. Now, this is an example of an amphipathic helix. So, this is your horse liver alcohol dehydrogenase, and you look at this helix. So, there is an amphipathic helix, and how do you know? So, the hydrophobic residues are these blue ones, these blue ones are the hydrophobic residues, and these residues are pointing inside, that means towards the protein, and the red ones, you can see these red ones, these are pointing outside, that means towards the solvent. So, that is how they are. So, there is the blue ones hydrophobic on the same side pointing inside, the red ones hydrophilic on the same side, they are pointing outside. Okay. Again, an example of an amphipathic helix. So, this is how the helix again is going to look like if I look at it straight through. So, this is, as I said, A is view down the long axis of an alpha helix showing the side chains. So, all these R's are the side chains. Remember, we had labeled them as R1, R2, R3, R4 like that. So, So, these arcs protrude away from the helix backbone. So, this is important. So, the way the helix arranges itself is that the CO and the NH groups, those main chains, they point inside, but all the side chains they are actually pointing outside. Okay, they are pointing outside. Now, this is your helical wheel. So, the helical wheel diagram, it shows a highly amphipathic alpha helix. Remember, we discussed amphipathic. It would be having both hydrophilic and hydrophobic phases. So, what would happen is, on one side you can see, as I said, on one side of the helix it contains numerous positively charged groups, which are the blue ones, which are these ones. So, R, arginine, Q, you should know what Q is, K, lysine, right. Then you have G out here, which is glycine. Well, is not particularly charged. So, this phase is essentially again a Q here. So, this phase essentially is hydrophilic phase. You go to the other side, you have F, L, what is F? Phenylalanine, right? L, leucine, V, valine, leucine, leucine. This is the hydrophobic phase. So, you have two phases, amphipathic. This is hydrophobic, this is hydrophilic. Okay. This is another example of peptide calcitonin. This is an hormone. You can see out here again. Here, the red ones, it's a different difference in color. The red ones you see leucine, 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 leucine. These are all the hydrophobic, amphipathic, right? Hydrophobic phase. This cysteine, lysine, right? What is GLU? Yeah, you're right. This is glutamate, lysine. This is hydrophilic, right? So, that means hydrophobic phase, hydrophilic phase. If you continue the helical wheel, again you look at this one. So, there is the group coloring. If you look at this helical sequence, what you see out here is the non-polars are represented by yellow, the polar uncharged represented by green, the acidic by this pink, the basic by this light blue. So, you can see what has happened is, on this side leucine, 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 isoleucine, leucine, leucine, valine, valine, all these are on one side, and all the polar or uncharged, all these like glutamine, serine, serine, all these are on the other side. So, that means this is the hydrophilic phase again, this is the hydrophobic phase. So, this has huge consequences, and hopefully we can go through some of those in the next class, but this is what a helical wheel is supposed to look like, and what the importance of it is that you can look at through down and look at the different ways that the R groups are packed. So, again this is another example. So, the first one, it is an amphiphilic helix. You can see amphiphilic means, well, you can have these are isoleucine, trip, valine, these are, it is essentially amphipathic, that means these are the hydrophobic, this is the hydrophilic. Then this is a non-polar. It is a non-polar. Why? You can see wherever you are looking at these are yellow ones, and the non-polar residue is essentially non-polar, and this is a polar because you have a predominance of these blue ones, which are the polar residues. There are other unusual helices. What we will do is, these other unusual helices we will talk about in the next class. Then we will look at some more aspects of these helices, and once we are done with these unusual helices, but just give me a couple of minutes, I will just I will just keep it for the next class, I guess. So, once we are done with this, then we will look at some helix packing, then we look at the second most important one, structural secondary structure, which is the better sheet, and we will go ahead and look at several combinations of those. Okay.